This is the second part of graphing trig functions. We're going to look at the tangent of theta right now. Now, you're used to sine being like this, cosine being like this, but tangent and cotangent are going to be different. They're going to have this kind of a shape. Okay, this one in particular is tangent, that one's going to be cotangent. Well, let's take a look now at what this will be. We'll use this. This time, though, we've been doing it in radians. I'm going to now make this 90 degrees and 180 degrees, 270. We'll do this for a while. Some of these it's a little bit easier anyway, but it also doesn't hurt to sort of keep it, I guess you could say, go back and forth using both. Now over here, well, here's the thing, that when we do this, we'll do this and then you'll see we have to do something more with it. Okay, so on this first one, we're going to look at the tangent of 0, and that's where you use a unit circle, and you'll get used to these with it. The tangent is the sine over the cosine, or the y over the x, so it's 0 over 1. So the tangent of 0 is equal to 0 over 1, which is 0. Now let's look at 90 degrees. In fact, I'll just call this 90, 180, 270, 360. So when we do the tangent of 90, okay, well, what we see is 1 over 0. Well, that's equal to 1 over 0, and 1 over 0 you cannot divide by 0. That is not equal to 0. That is undefined. So I'm going to put UNDEF, undefined, for 90 degrees. Well, then we're going to do the cotangent, oh no, not the cotangent, that's later. The tangent of 180 degrees. The cotangent of 180 is 0 over negative 1, which is equal to 0, because 0 divided by something is a legitimate number, 0. You can't divide by 0, so that's undefined. Well, the tangent of 270 degrees is negative 1 over 0, so we're back to this undefined. And then for 360, that's the same as 0, so we're at 0. Undefined on a graph is going to be an asymptote. So what we're looking at right now is that we have an asymptote here and an asymptote here, and there's a point here and there's a point here. Well, that doesn't get us to one of these kinds of graphs over here. So what we're going to need is we're going to have to look at in between these here. So I'm going to take this 90 degree to 270, and we're going to do 90 degrees and do the in-betweens. So from 90 degree to 180, in between that is 135 degrees. That's exactly in the middle. And then we'll do the 180. And then in between 180 and 270 is 225 degrees. And then we have the 270 degrees. Alright, so I'm going to bring these down like this and work with them there. So what we're doing is going in between here and in between here to find out what numbers here and here will let us do something other than just be at 0. So let's figure out what happens when we are right in the middles of them. So here would be 135 and here would be 225. Okay. So the tangent at 90, we already know, is undefined. The tangent at 135, well, the unit circle shows that at 135, y over x is something over the same thing. It's going to make that 1, and it's negative, so it's negative 1. Okay? So I have to write it as square root of 2 over negative, square root of 2 over 2 over negative square root of 2 over 2 is the same as 1 over 1, or 1. They cancel each other out, you get a negative 1. When we do 180, we already saw that that's 0. Tangent of 180 is 0 over negative 1. For 225 degrees now, we're going to see the tangent of 225 degrees is a negative square root of 2 over 2 over negative square root of 2 over 2. So the negatives cancel out. These become cancel out as 1 over 1, and we get 1. Okay, so I'll put a 1 and circle it there. And then for 270, we already know that that's undefined because it's negative 1 over 0. Well, up here now, let's graph this. At 135, we're at negative 1. 135 is this one, and 225 is this one. 135 is at negative 1. At 180, we're at 0. And at 225, it's at a positive 1. So that means that we're connecting these, but not with a straight line. We'll start at the bottom, and it comes up, and it curves towards these, and then it goes that way. That's what a tangent graph looks like. We'll repeat it so that we're going from pi over 2 to pi to 3 pi over 2. So that means this one and this one and this one, well actually it's this one, 5 pi over 2 will be undefined. We have to put the halfways in between here and go to negative 1 and positive 1, so it'll be just like this first one. I missed there a little bit, but it's still close enough you can tell it was. And that can be done along the lines. I could do it along here too. I could do it along there. I can do numerous ones. You're required to do at least 2 periods of it. So this is one period of it, and this is the other period of it. And we did it by breaking it down in between the ones that were given. That's the way a tangent one looks like. Now you can do a tangent on the graph. In fact, let's go over again how to do these on a graphing calculator. Okay. The first thing when you use a graphing calculator, number 1 is to change the mode to radians. Then second, you go to the y equals graphing part and graph it. Okay? And then 3, you change the window, or make sure the window is set. So that x minimum is a negative 1. X maximum should be 7. So that gives you from 0 to 6.28 or 0 to 2 pi. You have a little bit on both sides. X scale, set that as pi over 2, or set it as 0. Oh no, it's 1. I should write it this way, 1.5708. And then for the y's, you're going to do a y minimum of negative 4, and a y maximum of 4, and a y scale, let's keep this where you can see it, a y scale of 1. So the x's and the y's, and follow that for your window. So on mine, I'm on the mode of radians. I'm going to put in tangent of x. I'm going to go to window and see I have negative 1, 7. I put in pi over 2, and the calculator purposely changed it and didn't round it. Negative 4 and 4 and 1 for the scale, and the rest of it below this doesn't matter. Not for our purposes right now. And back to here, because now that I've done that, I can graph it, and you can see this looks reasonably like what I did. Here is pi over 2, that's the 90 degrees. And here is pi, and here is the 3 pi over 2, or 270 degrees. And so this shows one full one. Unless I change the scale or window, it would be, that's good enough to see. Let's do this now with cotangent. I'm going to switch to this paper here. And what we're going to look at now is the same kind of idea. We know that cotangent, if the tangent one went this way, the cotangent one's going to go this way. Okay, but now let's actually do it. Well, I'm going to do this as 90, 180 again, 270, 360, and that's as far as we'll go now, because might go further if we need to. Well, let's wait and see. Okay, so what I'm going to do right now on this is I'm going to come back down here. Well, you need to find out what's undefined, because it's not necessarily the same as the tangent. So for 90, 180, 270, and 360, okay, so I'm going to say the cotangent of 0. Well, the way you find the cotangent of 0 is it's 1 over the tangent of 0. That's how you're going to calculate it. So first we'll find, and even better is to use the reciprocal. So I'm going to show you that. The tangent of 0, okay, is equal to 0 over 1. I'm not going to put 0 yet, but I'm going to do this because I want to do the reciprocal. The cotangent of 0 will be the reciprocal, which is 1 over 0. So where the cotangent of 0 is 0, the tangent of 0 is 0, the cotangent of 0 is undefined. That means that this is going to be an asymptote. Well, in the other one, the asymptote was at 90. Well, 90, that's not going to be so here. The tangent at 90 is 1 over 0. Well, I would have written undefined, but for the cotangent, we're going to flip that. We're going to make it 0 over 1, which means it's 0 instead of undefined. And when we do tangent of pi or 180 degrees, we're going to get 0 over negative 1. For the cotangent, we're going to get negative 1 over 0, which is undefined. This would have been 0, this would have been undefined. So we're going to continue doing the same thing here. The tangent of 270 degrees is negative 1 over 0. So the cotangent is going to be 270 is going to be 0 over negative 1. Whereas this one was undefined, this one's not undefined. So it's going to be 0. And 360 is the same as 0, so we're at undefined here. So we have the same problem that we had with tangent. So we're going, but this time, because we've moved over, in fact, let's take a look and compare this. For the tangent, we had to work between 90 and 270 because that's where the asymptotes were. But for cotangent, it's between 0 and 180. 90 and 270, instead of being asymptotes, are actually zeros. So now, having done that, having seen that, let's use the in-betweens here of 45 degrees and 135 degrees. Those are the 45 in-between midpoints, I guess you could say, between the half hemispheres, semispheres. Figure out best word later. Right now, let's do this down here, where what we're going to do is 0, 45, 0 degrees, 45 degrees, 90 degrees, 135 degrees, and we won't need to go further because, oh no, we do need to do the 180, because this one we know is undefined, this one we know is 0, and this one we know is undefined. Okay, so we're going to look at the tangent of 45 degrees, and the tangent of 45 degrees is square root of 2 over 2 over square root of 2 over 2, which is just 1, or 1 over 1. Well, the cotangent is the reciprocal of that. Cotangent is therefore going to be 1 over 1, so it's going to be 1. When we look at the tangent of 135 degrees, we get square root of 2 over 2 over negative square root of 2 over 2, which is like a negative 1 over 1. Put the negative with either one of them. When we do the cotangent, it's going to be negative 1 over 1. It's still negative 1. It does not matter which way you set that up. So we have the 1 and the negative 1 to add it to it. That means here 45 is at 1, negative 135 is at negative 1. And then I'll make my curve here. I'm going to do the same thing with these. The 0 coming down here. And I have done 2 periods of this. Notice the differences between tangent and cotangent. Okay, I'm going to try to put these close to each other here so you can see. So number 1, of course, they like the flip of each other. Okay, now, having seen that, though, this one is going between 0 and 180, and this one's between 90 and 270. So not only do they reflect, almost like a reflection, they also move. So it's sort of like, to do this one, you'd have to move it all 90 degrees and do a reflection of it in order to make it the cotangent, or vice versa. All right, now having seen those two, we're going to take a look at the other 2 type of I say the other not as standard trig functions. We are used primarily to sine and cosine and tangent, pretty close with them. Cotangent, cosecant, and secant are not as common, but you should know them, so you get a chance to see them here. All right, so for cosecant, here are the ways to do it. Okay, number 1, you graph the sine of this. Graph y equals sine of theta, or x in our case. And then second, you're going to put the asymptotes at the zeros. And then 3, you're going to draw little parabolas. Whoops, P-A-R-A, parabolas. I did not forget to spell, really. Parabolas at the vertices. Okay, now let's do that. Okay, we're going to graph y equals sine theta. So y equals sine theta would have points at these spots. You can go back and look at the lesson on that if you wish to. Okay, let's make an attempt at a curve, a good attempt here, and I'm going to repeat it. So let's say that's a little bit above that where it probably should be, and then 0 and -1 for here. So now you see how I'm setting it up. I should have done this actually as a dashed line because this is not the actual graph. But what I did is I did sine theta, and then I'm doing the asymptotes at the zeros. So here is a 0, this one's an asymptote, this one's an asymptote. So the places where the sine curve hits 0 is where I put asymptotes. Okay, so having done that now, the third part is I just go to these vertices and I simply make a parabola. And these parabolas is the cosecant graph. This is a cosecant. So like tangent and cotangent, it's not continuous. It's stopped, they go up forever that way, but then you flip over to here and it goes down forever that way, and then up forever that way, and then down forever that way. This isn't really necessary for this, except for if you need it in order to do the sine graph. But the sine graph is only there in order to get these points. You don't even really need that if you knew where these points were. But this is what a cosecant graph looks like. Now let's look at a secant graph. I think you already have the idea of what this probably will look like, since it's going to be based, since the cosecant graph was based on sine, the secant graph is based on cosine. So we'll graph the cosine first. Okay, and the cosine started here, went to here, 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 and here. So this was the basic look of the cosine graph. And then I will simply continue it so that we get 2 periods of it. Again, I forgot to do it as a dashed line. Okay, Or I could have just gone to here and realized, oh, I only just need those points. Well, anyway, that being said now, I see that the places that are zeros get my asymptotes, and notice that they are in different places than the ones for the cosecant graph. But then I do the same thing. These are also parabolas. So secant and cosecant are both parabola-based, non-continuous, and so on. So there I did 3 periods of this one, simply by finding those points that were vertices for the cosine, and of course doing the asymptotes. I didn't need this for it either. Now let's look at a couple of variations of this. Okay, like with the other part of the lesson for sine and cosine, we're going to look at when the amplitude changes. What that means is that the cosecant was like this, now it's going to be like this, but this difference is going to be going from 1 to 3. Okay, so to do this, it will be better to come down here and actually do this as the cosine. Let's follow this. Cosine, 3 times the cosine of 0. So that means find the cosine of 0. And the cosine of 0 is 1, so 3 times 1 is 3, so we'll put a 3 here. For 3 times the cosine of pi over 2, well, that's 3 cosine, and let's use the unit circle so we get used to this. Pi over 2, the cosine is 0, so we just simply put a 0 here. Oops, I shouldn't even put that, I just put 3, 0. Cosine of pi over 2 is 0. 3 times 0 is 0. And then for pi, we're going to do 3 cosine pi, and the cosine of pi is -1, so 3 times -1 is -3. 3 times the cosine of 3 pi over 2, or 270, well, that's at 0, so it's 3 times 0, so we get another 0. And then pi over 2 pi and 0 are the same, so I'll put that 3 there. So now let's graph those points, 0 and 3, pi over 2 and 0, pi and -3, 3 pi over 2 is 0, 2 pi is 3, and so if I were doing that graph, I would do this, and then I'm going to repeat it here. This one's going to come down here, this one's going to come way down here, this one's going to be back to there. So I will do, oops, I should have made this more like that, but it's close enough. The rest of it, doing this once, so remember the first step was to graph y equals 3 cosecant, oh, not cosecant, oops, I made a mistake. This is cosecant. That means it's the sine curve that it's based on. Ooh, so I need to come back here and change these. Okay, so follow along, let's change it. And this is good to notice. You want to stop yourself with these periodically to think about the fact that if it's cosecant, it needs to be the sine that we graph. My mistake here was not writing this down first. If I had written this down as a step to remind myself, I would have recognized, oops, it has to be the difference. If that's C for cosecant, then it can't be cosine, it has to be the other one. So this is a common mistake. I just did it as an inadvertent example of a mistake to avoid. Well, let's fix this by coming back down here and doing sine of 0, which is 0. So this is 0. Sine of pi over 2 is 1, so this is 3. Sine of pi is 0, so this is 0. Sine of 3 pi over 2 is -1, so oops, this one's -3, and then 2 pi is back to 0. So over here on the graph, I am going to use a blue to do these. 0, up to 3 here, 0. This one's at -3, 0. So the sine curve, and won't do it dash this time just so we can ignore these other ones more easily. Up to 3, down to 0, down to -3, and at 0. So I'm going to continue this. Okay. Now where I was going with this, now that we have the correct sine curve, is the 3 steps are to graph the opposite of it. And then second, to do the asymptotes at the places where there are zeros. So I will now be able to get these correct asymptotes. And then third, do one more here, and then third will be to do the parabolas. And so there's one, there's two. I only need two, but since I have these pots, I might as well just do them because I like having it right. Oops, I can't do one more. So I have 4 periods there, but you need at least 2 periods for the graphs that I require in any assessment. All right, now that's dealing with an amplitude. That was the basic graph. In fact, the basic sine curve would have been like this. Let's see, it would have been up to pi over 2, down here, and it would have continued like that. Oops, I can't quite draw it right, but what happened is that the zeros, of course, is still there, but it's pulled up. Instead of at 1, it's pulled up to 3. Pulled up to 3. And that's what an amplitude does. Okay, the last one we're going to look at now involves changing the period. So we're looking at changing, or look at where the number is now. We're looking at secant 2 pi. So on the last one, and I just did, let me find that one again. Notice that for the amplitude, the number we multiply with or do something with is outside the function here. Here it's on the inside of it. So it will affect the amount directly. So here's how we're going to look at doing this one. Okay, so we're going to do it first. Y equals, now that's secant, so it's cosine of 2 theta, or 2x is what we'll do on the graphing calculator. I guess I'll put theta for now. So it's cosine of 2 theta. Then second, we'll put the asymptotes. And then third, we will put the parabolas. Okay, so here, let's come on down. So what I'm going to do is I'm going to do this as cosine 2 times 0. Okay, and I think I actually want to use some room down here for it. Okay, cosine 2, 0. Okay. And another example here. Nope, cosine 2, 0. Cosine 2 pi over 2. Cosine 2 pi. And cosine 2 3 pi over 2. Now you can make that pi over 2, that makes it pi. There's a number of things you can do with it, but let's try this. What I'm going to do is I'm going to say instead of, oh, I meant to do that, 2, 0. Well, 2 times 0 is 0, so that's cosine of 0. So when you multiply 2 times 0, since you get 0, we're just going to stick with the cosine at 0 is a 1. Okay, and that means that this will be at 1. Okay, now at pi over 2, that's 90 degrees. Cosine of 2 times 90 makes it the cosine of 180 degrees. And the cosine at 180 degrees now is at negative 1. And then we look here at pi. Okay, that's 180 degrees, so it's cosine 2 times 180 is going to make this 360. The cosine at 360, well, we're actually back to with 0. We're back to a 1. The cosine of 2 times 270, okay, that's going to make it 540, cosine of 540. And 540 is back to where 180 is. It's coterminal with it. So that means we're back to a negative 1. And 2 pi, well, if I multiply it by 2, I get 4 pi, or 360 multiplied times 2 is 720. That again brings me back to 0 or 1. So let's come up here and graph this. So I'm at 0. And pi over 2, I'm at, oh wait a minute, no, at 0 I'm at 1. I should have been more careful thinking about it. Pi over 2, I'm at -1. At pi, I'm at 1. At 3 pi over 2, I'm at -1. At 2 pi, I'm at 1. So it looks like this curves like this. Oh, that one's supposed to be up here. Again, I get that mixed up because I'm so used to putting things at zeros. So notice that this is one period, and then this is another period. Now remember, I'm going to overlay here the basic cosine one. The normal cosine one would have me going this way. So what happened here, if that's this one, it has been sort of crushed in and brought in like this. So this originally was this. So it's been squeezed in like that. That is what a larger number than 1 will do here. When you do 2 times or 3 times or 4 times, you make it, squish it in smaller and smaller. If it had been 1/2, it would have taken this one and spread it out doubly as long. Sounds weird, like the opposite of what the number means, but it does that because of what it does to the numbers here by spreading it out or squeezing it in, because it changes the numbers down here. Okay, so we have graphed 2 periods of cosine 2 theta. Now we're going to do the asymptotes, and that is the places where the zeros are. Now we don't even know exactly which numbers, but we can sort of make a educated guess that they are exactly in between 0 and pi over 2. So that would make this pi over 4, or 45 degrees, and 135 degrees, and so on. Now do the parabolas and go to the vertices, each vertex, and I can do a nice, well, can't say my drawing is going to get any awards for this, but and now I actually have 3 periods there drawn. In fact, for this one, I think I'm going to do a, let's find a nice big fat kind of marker to make it really obvious. These are the ones that are the answers to this. Okay. So the period is going to be one full amount or length of it, but the number, when you change it, you can either be spreading it out or you can be squeezing it in. And this time it's sort of squeezed it in. So now you have seen sine, cosine, tangent, cosecant, secant, cotangent, and some adjustments with when the amplitude or the period are changed based upon what's changed in the equation.